Okay,
welcome everybody. As you could make it, we have the pleasure of welcoming Xavier Vallvé, to this WISE set of WISE lectures. He'll be talking about, as you can see, hybrid photovoltaic power systems on rural microgrids, in which several of us are involved in rural communities here in Canada. So there's a lot of interest in his talk. The slides, by the way, will be posted on the WISE website after the talk, sometime after the talk. Javier is graduated from mechanical engineering at the University of Guatemala, so he's an alumnus of ours. By the way, he was this weekend here celebrating with his group, what, 35 years?
35 years. I had never seen them ever since. It was hard to recognize.
Yeah, correct. And got a master's in applied science in '79. In '86, he co-founded the engineering and consultancy company Trama TecnoAmbienta in Barcelona, Spain, where he's a partner right now. He has large experience in renewable energy and electrification projects, with several projects in various villages and places with microgrid connections, island microgrid connections in Africa, Asia, South America, and several islands, one of them in Ecuador, another one in Chile. By the way, we have a collaboration with the Chilean colleagues as well, who have very similar interests as we do. He has been a project director, lead consultant in several private and government for several private and government clients, and several projects, including several with the UN. He's a director and lecturer of the master's degree, Master in Ingeniería y Gestión de Energías Renovables at the University of Barcelona. He's a member of the scientific committee of the PV Hybrid and Microgrid Conference and the European Photovoltaic Solar Energy Conference and Exhibition. By the way, he's involved in several of the standard discussions for microgrids, which is a major issue in microgrids, defining this. He's a member of the 7 international standards committees, as I mentioned, and a chartered engineer at the Professional Association of Industrial Engineers of Catalonia. So, thank you, Xavier.
Well, please. Thank you, Claudio. Okay, well, thanks everyone for being here. Yes, as Claudio said, I studied here, but I moved back to Spain just after graduation. So my professional experience in Canada is limited to the work terms, essentially, which were very, very rewarding. And my talk is on this topic of microgrids for rural electrification. Although maybe it's mainly technical, I will try to bring out some issues also from economic and social aspects. And of course, with 1 hour is not enough to go in depth into this subject. So I will just try to share my professional experience on this, and I will show you some case studies in the PowerPoint, but also I have brought a documentary, a DVD of a project, which I think will also be very useful. So, well, we just a little bit of propaganda of this company. It's a very small company. We are 12 people, but it's very focused on rural development in electrification. So, in fact, we started in '89 with off-grid electrification in the Pyrenees, which are the mountains that are between Spain and France, where at that time there were still a lot of small villages and houses without electricity, without any grid. So that's where we started to deal with remote users and their needs and their lack of funding. But at that time, Spain had recently joined the European Union, so there was some incentive to look for co-financing for some of these projects. But from that experience, we expanded it to other projects in other rural areas of the world. So, as an initial reference, I introduced the concept of what it is an autonomous hybrid power system for a single house in southern Spain, but in southern Europe, it would be very similar to what you probably have here or in the US, where you have usually a PV generator, and I say usually because solar is the more universal resource, but of course where you have wind or you have hydro, you have to choose the one that is most cost effective. Typically you connect it to some power conditioning, which may include an inverter, a charge controller for the battery, and then you may have a feeder at DC at say 12 volts or 24 volts to feed some appliances, and then an AC feeder for most of the appliances. And in fact, when we started the first projects, we would do most of the installation in DC because it's more efficient, and just some of the outlets for AC. But it became the market was not large enough for DC appliances, so it was too difficult to have a customer, a remote customer looking for a 24-volt CFL bulb. So for some years we have been doing mostly AC, all AC, but now we are coming back. Now, because now with essentially with LED lighting, with laptops, you start to go back to having a DC, a part of the house in DC. So this is a typical house in the Pyrenees, houses where the settlement is from approximately the year 900, the year 1000, although the house in its shape, it would correspond to the 15th to 16th century, depends on the site. And usually they are scattered houses 2 to 3 kilometers from each other, so a very self-sustained economy. And in this case, they have gone from the 19th century to the 21st. So the grid never reached those houses. Sometimes the battery room, if you can manage to make it accessible from the outside on the north side, is very good because you can keep them cool and good temperature. And this would be your power conditioning equipment. Another experience was in 90-something, 92, 93, a village. That was our first village in the south of Spain, La Rambla del Agua. Small village in Andalusia, which is this village. And, well, you don't see very well, but this is the PV generator there, and this is the mechanical room. And that's when we started to face the social issue that I will explain a little bit further on, of trying to share a limited resource in a village, which it's not new because this had been done over the ages with the water resource, but it's new for electricity because we have this culture that electricity is something that we can use as much as we can, as long as we pay at the end of the month. But we are not used to having a limitation. Another change that we have gone through is going from interim to permanent solutions. PV in the 90s was an interim solution waiting for the grid. That was the concept. And in fact, this picture, it's also from the Pyrenees, but from the French side. The French model is of a state-owned utility, EDF, Électricité de France, that has the concession of all the land and has the right and the duty to bring electricity. So EDF, on remote sites, started to install those kits, which now, well, you can see the old type of cells, round cells and so on. And they were a small system just to provide very basic illumination, saying, we install this here, we are going through permits and and through everything that is required to bring the grid, and we will be able to reach you in a couple of years, say. Well, in a couple of years, EDF installed those type of solutions, standardized 3 kilowatt peak solutions, and said, we will never come with a grid. This is what you get, and you pay your minimum bill invoice to the utility, and the utility operates it. And this is in the Spanish side, not on the French side, but still, in this case, not because of a state-owned utility tells you this is what you get, but basically because you have no other choice. So a typical house, installing the PV generator on the roof, which is more, now we call it building integration. At the time was just putting it on the roof so that the thieves don't get it. And this is in the Balearic Islands, in Ibiza, where you are in an island, so it's interesting to combine PV with a small wind turbine generator. So from the technical point of view, it's a system that has some generation, storage, transformation, management, and consumption functionalities. And you have to try to measure and inform at some level, whether it's informing the operator, that is the consumer, or informing an operator that could be a utility or a cooperative that looks after the service, and you have to control this. Now, we could call this part the PV or the renewable energy micro power plant, and this is the distribution, which could be the wiring in the house. And this is, everything is in the consumer's premises. But this distribution is what we will see, that it could become more, it could become larger and then feed several users. And that's how we slowly went into the microgrid concept. So we have gone from individual houses to villages, to hamlets, bottom up, as opposed to smart grids that are becoming microgrids from the top down. At the end, most likely, a lot of the solutions and the schemes will meet, but right now there is the two paths. Which means that we saw that the needs in a European efficient home, still with lighting, audio, video, refrigerator, household appliances, washing machine, ironing, freezer, and odd jobs, those needs require a certain size plant, that the same plant in a rural area in a developing country with lower needs could fit a multi-user microgrid. So initially, the plants were not designed for a small hamlet in a developing country were not much larger than the plant that you'd have on a farmhouse in Europe. From the electrical point of view, there is a lot of discussions, which I don't think they're that relevant, but I will just point them out to you, as to whether we should go to what is called an AC coupling. That means that the different devices are interconnected through the AC feeder line. It has certain advantages and it has certain disadvantages, and this is the typical diagram where you have this AC bus that also feeds the loads, to which you connect different generators through inverters, and then if you need storage, you connect through a bidirectional inverter. And then there is the more traditional DC coupling, where everything is coupled to a DC bus bar, and then you have the inverter to supply the part of the loads that are in AC. Sometimes I think a lot of ink and words are wasted debating between the two, and I think that is not that relevant at the end. There are other more critical issues, and both solutions, if they are well designed, are acceptable. And probably from the efficiency point of view, there is ones that are better than the other, depending on the load profile. And many projects end up with a combined solution, that part of the components are coupled in DC and part are in AC. So in our rural world, we call a microgrid typically up to 100 kilowatt or kVA. But more than the power, it's the concept. Usually is a microgrid where everything is low voltage, where you don't step up the voltage and have long transmission. So it could be 100, but it could be 200 if you have a lot of distributed generation. But that's the order of magnitude. And there is still a lot of R&D required, not only on the technological aspects, but on other aspects like we will see of business models, load management, etc. There is relatively very little regarding international standards, but there are guidelines and specifications which we did not have 20 years ago that are now available from different IEA research agreements and IEC. So in the design approach, the demand analysis and management is a key issue. I would say is the most critical, because where you underestimate or overestimate the load, everything that you design from there on will not match the need. And when you aim at technical solutions that have, say, typically more than 70% of renewable energy fraction, then you need good supervisory control, and you have to manage the battery and so on. So it's not the same to have, say, a diesel-based microgrid where you just have some renewable to offset fuel consumption, than if it's essentially a renewable energy operated, intermittent renewable energy operated microgrid, where the genset may be present only as a backup many times. And also when choosing the technology, it's worth to think that it's a technology that should be dealt with in a 10 or even 20-year horizon. That doesn't mean that the components necessarily have to live 20 years, but you have to foresee replacement if necessary. You have to foresee that things are easy to transport. And always monitoring, a little bit of monitoring, well, especially we are engineers and we like to get feedback, so if possible, always put a little bit of monitoring. This is a recommendation, which you don't always get the funding. Sometimes the donors or the client does not value this. So, as I said, other aspects is this DC or AC or combined coupling. Decision on the voltage, you will see that many batteries you can operate at at low voltage, up to here it's up to 600 volts, in Europe it's up to 1000 volts, but we try to stay below what is called extra low safety voltage, which is in Europe less than 75 volts. I think in North America it's 100 or 110, because you always end up with the risk that an unqualified technician tries to play with the DC bus and the batteries in these rural settings. Typically, one uses lead-acid batteries. One of the most common technologies is what's called tubular, but essentially it's deep cycle batteries, high depth of discharge, and an autonomy in the order of 3 days of the rated load. Charge controller for PV. Nowadays, most of the charge controllers are what's called maximum power point trackers. The inverters can be now bidirectional or even dual mode, meaning that they can be voltage generators or current generators, and different renewable energy generations and data logging. And this is another issue, the supply to the loads. Most people are used to having gensets which are three-phase, but in reality, very seldom you will find a three-phase load. So the recommendation is to use a single phase. And load management, user interface, load disconnect, all those are issues which are relevant in microgrids, but in rural microgrids they are critical. Another debate is, should we have individual plants or microgrids? And there are advantages and shortcomings in either. But if the village is relatively compact, it's better to have a microgrid because you have a centralized mechanical room, or maybe two, where you can do your maintenance of your batteries, your equipment relatively easy, instead of having to go house by house and into the house to inspect the components. And also, the fact that you share an inverter for the whole village means that you have the capacity for surge power for any house, where if you have individual systems, you need to oversize the inverter at each house so that they can handle the surge power of any appliance when it starts up. But nevertheless, there are shortcomings in that you have to see if that village has a certain social togetherness that will be able to manage a resource that is shared by everyone. So sometimes you may find a village that is in permanent conflict between neighbors, and it's better off to go to individual solutions that don't get burned in the mess. So a challenge is sharing this energy available without conflicts, which at the end becomes an energy distribution and metering issue. And why these type of solutions have certain value? Because in many rural areas of developing countries, or even in rural areas of developed countries like Australia, some parts of Canada, the US, there is a low population density and a low demand of electricity, high cost of grid extension, high losses in the transmission lines. So all your idle losses of your transmission lines and your transformer, if at the end of this very long line you have very low consumption, the relative weight is extremely high. So that may mean technical losses in the order of 30 or 40%. And but there is this difficulty that there is lack of adequate business models for decentralized electricity. Even countries, African countries that have electrified only 10–15% of the population, have mimicked the concept of a heavy, overstaffed, centralized utility in the capital that has to reach out to all the countryside, and they are not they don't have reference of business models more decentralized. So the vision is not either individual solutions or microgrids. The vision is in a certain village, maybe a combined solution with a microgrid for the center of the village, where you have the health center, the schools, and so on. Maybe another one in a farm that has a lot of activity and has several houses, but also individual solutions if the houses are scattered, but all of them under the same operational scheme. So if you have a tariff system, if you have a maintenance, they are all part of that operation. Well, this is a summary of what we mean by the rural microgrid, or the MSG, microgrid with solar generation. The fact that you could have several sources of energy, batteries, power electronics, but also that you provide service 24 hours, 7 days a week. So it's not like many villages that have gensets typically 6 hours a day or 11 hours a day. This is good quality service, but also it's a challenge, because if you provide 24-hour service, that also can give the feeling to the consumer that there is no limit to the resource. Here I want to share a study that we did quite a few years ago. Well, you can download it from a World Bank publication, but at that time it was modeling with a discount rate of 5% and a cost of fuel at site of €1 per liter. But when I mean site, this is a village in the Amazon region. So the liter of fuel there has had to go through several operations and finally arrive to the village in a small boats of 200 liters, drums. But the thing here is that it was an existing village that was already operating with a hybrid genset PV solution and batteries, and the idea was to use this existing data from this village to, at that time, extrapolate either way to have reference costs and to understand a little better the cost structure of the operation. Okay? Now, if you do it again with today's numbers, it would change quite a bit. First of all, because the price of PV modules has dropped by a factor of 3, and the price of oil has gone up. But I just want to use it as to bring the issue of the cost structure. So essentially, here what we did is, this is a village with 340 households, is to break up the cost and calculate a levelized cost on a 20-year horizon per kilowatt hour. And with direct genset and batteries only, genset batteries and 25% of the energy generated by PV, 80% or 100%. Okay? So essentially what you see at that time is that, okay, you could say 25% or 80% is lower, but in the order of magnitude, the levelized cost is very similar. Okay? More or less, we are always talking in the order of 0.9 euros per kilowatt hour. But if you separate what is investment, payback of the investment, operation and maintenance, management, and fuel, you see that though the total value is the same, the structure is quite different. Here is the fuel that dominates, and as you introduce batteries, you have better efficiency, and it goes down a bit, but then your investment payback starts to grow. until the more extreme case where if you'd had a 99% PV solution, it would all be payback and operation and maintenance, no fuel. But the issue is that there is a limit to how much you can charge to the consumers, the willingness to pay of that rural population. So typically a family, an average family can consume in the order of 20 kilowatt hours per month, which is very little but has a lot of value, but pay in the order of 8 to 10 euros typically. That's stretching it a lot already. So what happens is that if your willingness to pay is here, if you introduce renewables, at least the operation and maintenance can be sustained by the tariff, and part of the investment can be paid back. With a diesel genset, and this is what we are seeing in many countries, in many remote areas in South America and Africa, although the investment was given away, it was made by government, they installed everything, but they create the cooperative, but then the tariff cannot sustain even the fuel. So you end up seeing how these things are eventually abandoned, or they just turn them on weekends, or they collect the money and they run it for a few days, and they become not sustainable. So although the need for public investment is a barrier, it is also an advantage, the fact that the operation and maintenance costs can be reduced a lot. Okay, so now I will make some comments on demand or demand segmentation. When we see the amount of energy that we are talking about is extremely low, what we have called category A, or very low energy demand, which is essentially light and a little bit of television or radio occasionally, we are talking about less than 1 kilowatt hour per day, 550 watt hours per day. And B, which is, or it would already be, say, a well-equipped household with high efficiency appliances, is in the order of 2 kilowatts. And well, C would be other type of services like schools or a very large house. So we are talking about very, very small amounts of energy if we compare it to our average consumption here. But energy that has a lot of value to the consumer. And that's why I give also a lot of importance to monitoring, because we are talking about such small quantity that if you make an order of magnitude of error when sizing or when estimating it, you run into problems, and it's important to learn from the projects that are done. Typically, this is data in PV. You normalize it with respect to the PV capacity, so this normalized data allows you to compare small and large plants, and it would be typically, the units are hours day. So on a monthly average, you would have the blue, which is the reference yield or the radiation in watts per square meter or hour peaks. In green is the generation, and in red is the consumption. But you could have it also in hourly values. So I change a little bit the subjects now to introduce other aspects which are important: ownership and management, load management, invoicing and tariffs, and future expandability. So for business models, one thing that I have not seen is any miracle saying we do a little bit of funding for this infrastructure, and then it will generate enough revenue to be able to grow. Well, if this has not even happened in the Western world, the infrastructures are built by the state, the roads, it's not that you put a fee to your road, to your driveway, and with that money you will be able to build the next street and so on. I think it's legitimate to expect that these infrastructures partially need and deserve public investment. But this public investment can be reduced in the long run, because I have shown that you can generate enough revenue to pay back some of the investment. So it can be co-financing, and also costs are going down. Whether the ownership scheme is of a large operator, of a large utility, or a local model, you always need to establish some kind of local ownership, or the feeling that it belongs to the users, because at the end they are the ones that have to take care of it, because the infrastructure is in their village or in their home. And well, you have other aspects which I'm noticing that the time is going fast, and I don't want to extend too much, because I have some case studies I want to show. So the business models essentially is community-based, local cooperative, local ownership, local rules. Private sector, somebody coming in, doing a business, charging a fees, getting funding. Utility-based in countries that have provincial or state utilities, or many times it's a combination of those three above. Load management, what is the interest? You have to protect your battery, so you have to disconnect the loads when your battery is running low. So that is a technical issue. But another problem we are facing is standby loads. Standby loads, as the efficiency of appliances increase, also do standby loads, and you don't see them and they don't give any value. So in a lot of these villages with very small loads, the fact that you have your TV on all the time introduces a standby load that is larger than what the TV consumes when you are watching it. And the same with antenna power sources and a lot of other devices that we have. Other aspects what are important is that since the power source is intermittent, sometimes you are short of power, but sometimes you have surplus. So the fact that you have identified some deferrable loads that you could turn on and provide value at low marginal cost of electricity is also very important. And not only deferrable loads, but even ballast loads. You can get value from ballast loads. So the challenges related to demand are social aspects, trying to understand very well the needs and to distribute that resource. At the individual level, in each household, how you create awareness that some loads can be turned on for free at certain hours, and to manage each user independently, so he's not affected by what the neighbor is doing. Guide that consumption, and then from the techno-economic long-term sustainability, for example, there was a large program in South Africa which apparently was going to work very well because it introduced the concept of prepayment. But that is prepayment of kilowatt hours. But if I'm not too wealthy this month, I don't buy kilowatt hours. So the planned cost is still the same because you have to pay back the investment. You don't have a reduction in fuel if clients do not consume, and you still have to do the maintenance. So the concept of paying kilowatt hours is not appropriate. You have to try to avoid uncertainty in your revenues. And the best is to get a commitment of a flat rate according to each family, which they also appreciate, because they say, well, I have my budget, my energy budget is $5 a month, or 3 or 8, depends on the contract that I do. Okay, and the aspects of batteries and inverters and so on that they have to operate in the design range. So even information is a very good feedback loop. This is a housewife in Mallorca, in the Balearic Islands, that has a small display that makes her happy when she sees that the state of charge of the battery is high. And this is no, Modbus or Zigbee or nothing. It's just a display in the kitchen, right? So the impact is that you can really see, if you correlate the daily load and the weather, the resource, slowly, with only that, they learn to get most out of it. And you will see then that this is the design load, the horizontal line. On sunny days, they learn to do a lot more things, to put on the washing machine, pump water, water the garden. And on less sunny days, they refrain the load to keep their batteries in better shape. And this is only the right interface with the user. So it brings us to this concept, which is what I call the energy daily allowance. It's an allowance of watt hours per family. It's not as much as you want. Just you have a finite watt hours per day. That in reality is not watt hours, it is units. So I'm giving you units per day that if you manage them better, you will get more watt hours from those same units. If you manage them worse, you will get less watt hours. But it's like giving you coupons or something like that. This concept has been very successful. In fact, it started in that village of Rambla del Agua many years ago with many assemblies with the neighbors, and that's how the concept came along, but it has been improved at every project, and it introduces flexibility, but you pay a flat rate for a certain amount of EDA daily. In the last before we used to implement it, with meters and somebody reading and checking and like a police in the village. But now we do it with a device we call electricity dispenser, which is an electronic meter that has an algorithm inside. It measures, but in reality, it will cut you off if you exceed your allowance, because it has a 40 amp bipolar switch that you can program by software to. Typically, it will cut you at 600 watts or very, very low power that you contract. It has an auxiliary switch, smart switch of 5 amps that you can activate some deferrable loads. And it has a magnetic card that you use to change the settings or as a prepayment, but not prepayment of watt hours, prepayment or payment of days of service. I will not explain the full algorithm, but I will just go once through the concept. What you see on your display is, say, a water level, if we do a hydraulic analogy. I studied mechanical, by the way, that's why I need these analogies. So you see the level in units of your tank. Your tank has a certain capacity. So if you do not use all your daily allowance, you can store, but you can set the maximum tank capacity. So you could say, I will not let users store more than 3 days, or 6. So if you do not consume, you see the level going up, and if you consume, you see the number going down. If you consume a lot, you're cut off, but you're not cut off until the next day. You're cut off only for a few seconds, because there is always this trickle that is filling the tank that is proportional to the tariff that you have contracted. So really, it's not that you're punished you are guided. You are more guided than punished in reality. Because as soon as you are cut off, you reduce a little bit you turn off a few of the appliances and you see that you recover again. So you can add a Modbus communication and then according to the plant status, you could change the price of that electricity. So each unit or each watt hour could cost 2 units or 1 unit. So it gives also that flexibility. And you could also limit the power. If the microgrid is reaching the maximum power of the inverter, you could reduce the maximum power to the houses. And then we come to what happens, this is in Bolivia, when you have a larger village. What do we do? So we could go to a larger plan and then introduce transmission, high frequency. But the issue that I think that in the next years we have to work on is this concept of interconnectability. You could end up also with a village that you have a microgrid here that grows, but then you have another one that is a little at the outskirts of the village, a third one that interconnects these houses, and maybe, you know, one day the village keeps growing, the demand keeps being large enough, and you should be able to do this. Should be able to interconnect the distributed generation and storage and operate it all in a certain optimized way as a cluster of microgrids in reality. Okay. So this is what I think that should be the trend. This is my explanation of the issues, and now I have quickly some pictures that also I think you may like. I don't know if you want to have a couple of quick questions, or I carry on.
Please carry on.
Carry on, okay. I'll show you a microgrid in Morocco, in Senegal, in Cabo Verde, and in Palestine I will show you a DVD. So this is the example in Morocco. It's an isolated village in the mountains north of Morocco, not the Atlas, but the Rif. So here the thing is that since in this case it's PV, doesn't make noise, you don't have to put the power plant far away. You put it in the middle of the village, besides the mosque. So you start to have a competition here between the mosque and the solar PV, or the church. And this is, well, this is a picture not of the whole village. There are a few more houses up here, but you can see here we call it the Casa de la Luz in Spanish, or the Dardau in Arabic, house of light. But also, since you use up certain surface, you can have some spare rooms to have, it becomes a community center. In this case, it became for alphabetization of adults at night and for crafts for women. So, well, here is some data, very small, 5.6 kilowatt peak. But this provides electricity to quite a few houses. Some details on the construction, and this is the school. The distribution line is underground, which is more expensive in theory than aerial overhead, but in reality it's not, because the trenches, you have it's the contribution of the neighbors. So that means that they get involved, they feel that they are contributing, and if they don't dig trench, they don't get connected. It's as simple as this. So you end up with a better installation. It's underground, better to maintain, less risk of stealing electricity, and this is what it looks like. Okay. The maintenance is supposed to be done by the user that is elected, called the caretaker. So you can see here he doesn't have a large enough broom, so only the bottom part of the modules are clean, the top have a little bit more dust. But this is... So here we had a grant with a university on a research project, so we were able to do an assessment after 1 year. Many times you do a project and it's very hard to go back and do an assessment. So there was a performance assessment, technical, but also social, you know. Blackouts, monthly fee, are you satisfied? Do you know where your money goes? Because we created a users association, so the money goes under the pillow of the secretary of this association. But what is very interesting is that, you know, do you know where your fee goes? And 73% say yes, you know, this is better than us in the Western world. We don't know where taxes go. So they participate in the meetings. So not only the project of the microgrid had the value of bringing electricity, but it was a school of governance. The first time in this village, they had to create legally a body and have a bank account and elect somebody that's going to keep the money under the pillow and so on. This is another example in Senegal. In this case, the most valued thing is water. So the microgrid provides to the school and health center. They did not want lights for the houses, but only public illumination and water pumping. So here you have in this picture water tank and the street lights, which is very good because it's very complementary. In the rainy season, the water level is higher, so you need less power in the pumps, and you have less sun. In the dry season, you pump from deeper and you have more sun. This last example is from Cabo Verde, which is an island state off the coast of Africa. And this is an isolated fisherman's village, Montetrigo, which you can only reach by boat from this other village, Tarrafal. So it's 1 hour to the nearest village, so really it's remote. 600 people, 80 houses, of which only 60 said they wanted to connect. 20 said, no, we don't think it's going to work, so we'll stay. We don't know. Okay? So it has a hostel, several shops. It has to feed the telecommunications repeater. And as deferrable load here, it was agreed between everybody that they wanted an ice making machine, ice shavings, because they can, if they have that ice, they can take their fish to sell it to the next island, which is 5 hours away by boat. So if they have a good catch, they can put that catch in ice and sell it to a market where they get more value than selling it to Tarrafal, that is 1 hour away. So here the ice making is made only on days that there is a lot of sun, and it has to be made with the surplus energy. The electrical configuration, in reality, it's an AC-linked double DC bus, because the battery had to be so big that it's 2 DC buses, but the inverters can act as master-slave, so you could really take a little bit more from one side than from the other. The distribution grids and the characteristics, it's 27 kilowatt peak, large batteries, and well, here is the role of the municipality. That is not the village. Municipality, it would be larger. Is the legal owner. The tariff is a private company. It's Aguas de Porta Preta. It's a water company, a public-private partnership in the island that has a desalination plant and operates the water service in another village. And then the maintenance is done by the private company, and the basic upkeeping, it was 2 caretakers that were selected by election in the community. Well, here is a chart of the different tariffs. Here we calculated a tariff, a monthly tariff for each daily allowance, for each EDA. But finally, they chose another one, a little bit lower. But still, it's a tariff that will ensure sustainability. A few pictures, added value, for example, instead of hiding the PV generator, we put it in the school backyard to provide shading for the students. We noticed that at the playtime they were hiding because it's sunny and no shade, and it has given a lot of added value and also visibility to the students. They know that this canopy makes the electricity for the village. Also, to engage the users, as opposed to come with everything prefabricated and put it all together in a couple of weeks. So all the material had to be transported by boat and loaded by the consumers. The ladies were doing the mortar. Here they were the helpers of the bricklayers. And the batteries had to be transported one element by one element uphill from the beach on this, like a procession in southern Spain, Okay, the mechanical room, the large batteries, training the caretakers, the genset, and also the transportation of the poles for in this case it's overhead lines, so wooden poles, very practical because they pull them from the other village. The user interface, the electricity dispensers, the cards, and also after a few days we noticed how the users were learning to manage to flatten the demand curve. You see here your basic load curve in red, like this, and after a few days it becomes like this. Because things that they were turning on in the evening, they say, no, in the evening it discounts more units, let's turn it on during the daytime. And they manage. In this case, it's not only information, but it's also that the tariff changes. When the red light is on, it's double price. When the green light is on, it's half. Half price in units, the same amount of money at the end of the month. So we see that we have a very stable aggregate load, which is what we were looking for. And you see, well, this is difficult to explain, but essentially this is telling you, this is the number of days of autonomy that the dispenser is showing to the user. So you can see that the user is looking at the display because we advise them to keep more or less the level of that tank at 3. So they kind of look, and if they are above, they can consume more. If they are below, they consume less. And this is a cash flow analysis of a 20-year life cycle. With the tariff that we calculated, we could pay back 25% of the investment with a discount rate of 8.5 and still have a little bit of net present value of 13,000 euros at the end of the 20 years, which is not too bad. Now, with the tariff that they finally chose, this is what they have. So really, with the 25, they will not recover the 25% at 8.5. If you apply these economic values, it's not sustainable. But the reality is that they don't have to make an 8.5 discount rate because the 25% has been paid by the municipality, and the municipality only wants to recover it slowly through the tariffs, which they will. So this is only because we have applied this 8.5%. But still, with this lower tariff, they are able to replace the batteries when they have to be replaced. Okay, and this is it for that, and now I will show you this short DVD. Thanks. The DVD, okay, it's in a remote village which is 150 meters from the grid, because in some places remoteness is political, and in this case is in the West Bank, in the occupied territories in Palestine. So it's a political barrier. But although the film, you'll see the context of a village, small village, which was there 100 years ago and still there, which is besides a settlement now that wasn't there 5 years ago, where you have houses that look like Canadian houses with swimming pools and so on, and a nice road that you commute to work to Israel every day, and the other road which is in bad shape. But this is not, you will see it, but try to abstract a little bit from that, because what I think is interesting here is to see the impact that a little bit of electricity has on a rural family in general. So that's why I think it's more, although the setting is a little complex. The guitar music was done by some Israelis, so there is a little bit of hope of collaboration.
تصير بها على المنطقة هذه. وقدموا الكهرباء منعت عليهم إسرائيل، قالوا الكهرباء ممنوع تمر على الخط.
Now we are here in Tunisia. It's a village about 50 kilometers from Yatta, or 70 kilometers from Kharkiv. And now we are trying to analyze the situation here in Tunisia and implement a new project for an electrification of this village by using solar energy.
First we came to visit the Al-Khalil area and we looked for several places to see which place is most in need for electricity, and we found in Nazel. Like Nazel is, as you see here, it's a very poor and marginalized neighborhood. Even the Palestinians don't know about this neighborhood and if it exists or not. And as you see, like in the settlements just nearby, they have everything. And they didn't want to provide, they don't want to provide this neighborhood with electricity. Actually also water, they don't have water in this village or this neighborhood. They depend on collecting the rainwater in winter in water wells. And they use this water during the summertime. يعطيكم العافية. لا ما فيش ولا غلبة. المشروع هو عبارة عن توليد الكهرباء عن طريق الطاقة الشمسية، نستخدم الشمس لتوليد الطاقة الكهربائية، مش زي أي نظام كهرباء عادي يعني بيكون في أسلاك جاية من موتور كهرباء ومولد كهرباء وبدون كهرباء للدار، لا، هذا النظام مختلف. هذا النظام عبارة هو عن خلايا شمسية، هاي الخلايا الشمسية بتشبه النور تبعين النهار الشمسي. عن طريق هاي الخلايا الشمسية نوع ضوء الشمس بالضبط صح، ضوء الشمس بيجي على هاي الخلايا بيتحول ضوء الشمس لكهرباء. هل في تاخذوا كمان ايش في كمان طرق برضه ممكن نوفر فيها الكهرباء؟ ضوء، كيف الضوء ممكن نوفر؟ يعني عندنا ثلاث لمبات نقدر نستخدم وحدي وبلاش نستخدم الزلام كلهم، يعني مالناش حاجه اللي بنخبيه اليوم نلقاه بكره، بجد بيجي كل ما وفرنا اليوم ضل عندنا على طول الشهر كهرباء وضل باستمرار، يعني ان شاء الله متريحين على الكهرباء.
بالنسبه للكهرباء، لان الكهرباء بتحل مشاكل كثيره. فيش كهرباء، فيش كهرباء تطلع مي من البير اللي ما تغسل، فيش غسالة، فيش يعني تلفزيون هذا صار هذا في تلفزيون بقعد بشوف ساعة ساعتين وبنسى.
contra l'energia que ha de comptar cada dia i que talla per intensitat màxima i també amb les instal·lacions també funcionen correctament.
This, you will see that comes down a little bit. Okay, you see, it is 200.
I aquí acaba, doncs, diguem, el procés d'instal·lació d'unes instal·lacions que els donaran la llum, però a partir d'aquí no s'acaba ni la nostra feina ni la feina de la comunitat. Vol dir que a partir d'ara la feina la seva serà seguir molt de prop el projecte i seguir molt de prop l'evolució i el procés que viuen aquesta gent ara que dona electricitat, perquè no és una cosa fàcil. كنت اقعد وانا البس شوي كنت بشوش في غسيل المقابله النهائي يعني في الليل يعني عشان في ضوء بيقروا كمان بشوف شغل البيت يعني في الليل بتريح في النهار كمان يعني بقعد الاول كان دائما طول النهار شغل في الليل ننام المغرب يعني وما نعرفش ما في شغل في الليل بس الحين لا نقدر نشتغل في الليل شوي نقعد نريح نشوف يعني انا بغير مش كثير من هنا.
Well, okay, so.
Okay, thank you very much.